The Word document weird. It helps if I turn the TV on. And I'm going to try and remember this time to put the receiver in for the clicker. He decides to pull up. There we go. All right, let's get started. What y'all think of the ZX assignment? That was easy, but it was supposed to be. It was supposed to be because really, I mean, I just want to make sure that that you generally understand the process by which you need to compute ZX. And I will tell you that, to be honest, we really won't be computing ZX all that much directly, but I think it's an important skill to be able to do. So it might show up on an exam, but it probably isn't going to show up in any more homework assignments. So, but the cool thing about it is, if it does show up on an exam, it's easy. Like, it's really not that hard. Just find the line where the area above equals the area below and just start summing moments about that line, and there you go. Okay. Today, what we are going to do, so I would argue that the last lecture is really just sort of setting the stage for some of the background theory about beams, but now what we need to do is we need to get a little real. So today what we're going to do is we're going to discuss beams more specifically. And what we're going to do is we have two different classes of beams that we're going to assess. Those are continuously braced beams and discretely braced beams. And so for continuously braced, first we'll learn how to analyze them, then we'll learn how to design them, and then the same thing with discretely braced beams. But so part of what I'm doing today is discussing bracing and trying to make sure that you understand what I mean by all that. So let's get into that. All right. So what we're going to be talking about today is the effect of bracing. And then we're really specifically going to be talking about the role of a term called LB. LB is the unbraced length for a given segment. This is a term that I think sometimes students confuse a little bit, because the unbraced length is not necessarily the length of the beam. Those aren't the same things. And so making sure that everybody understands what the difference between those two are is important. And then we'll get into analyzing a continuously braced beam. And by that I mean, given a beam, making sure that you can assess that it has adequate capacity. Now, as I was mentioning a little bit before class today, one thing I'll say is that today we're going to be doing a lot of referencing in the manual. There's at least two design aids that are going to be very important. One of them you've kind of seen before, if you remember, because we discussed it near the tail end of structural analysis last semester. But we'll get to that here in a little bit. Okay. So let's just make sure everybody's on the same page. So what we were talking about yesterday was theoretically the maximum moment that a beam can withstand, and that's MP. And when I say theoretically, what I mean is really the effect of bracing, which is what we're going to talk about today. Now, in order to compute MP, we just sum the moments, which is the force in each plate times the distance from the center of that plate to the plastic neutral axis. But since the forces are just Fy times the area, we have the same Fy across the board. We just factor out the Fy, and now we have a new section property called Z. Okay, and so that was really sort of the focus of the example and the homework that you did last time. Now, what we're going to do now is we're going to discuss continuously braced beams. Let's take this slide and digest it a little bit. Now, for steel beams, I want to be clear, the maximum possible capacity is MP, okay? And I don't care, I mean, from here on out, I don't care if we're talking about continuously braced beams or discretely braced beams, that is the maximum possible capacity. And when I say maximum possible capacity, I mean the maximum capacity that we can count on for design. Now, I want to be clear that that's not the capacity for every beam, it's just the maximum possible capacity. See, what makes things complicated with beams is buckling. Okay? Like columns, beams contain elements that are in compression, and things in compression like to buckle. And so if you have an element that's in compression, you have to account for the section stability. Okay? And the other thing, like columns, is that a beam's capacity is a function of the distance between the braces. Okay? Now, what we have a term for that, and we call that term LB. So LB is the distance between braces for a beam. Okay? And so that gray box there on the right is very important, that there is a difference between how long a beam is and what is its unbraced length. Okay? And I'll show you a picture of that here in a bit. Now, I want to make sure that everybody understands what I mean when I say bracing. Okay? So I have here a couple of examples. Here on the left, this is one a little bit more near and dear to my heart. This is an example of a highway bridge superstructure. Okay? Now, one thing to note is, this doesn't really affect the explanation, but this superstructure is on a skew. So that means you have some beams that are in front of the other. So it's like the road is going this way and the river is going this way. So the bridge has a skew to it. So that's why you can see the girders are sort of a little offset. Okay? So we have 4 I-shaped plate girders, okay? And then between those girders, we have a series of frames. We would call these K-frames because you can kind of look at the way the angles are and they kind of form like a little K. But each of these cross frames, so sometimes they're referred to as cross frames or diaphragms, but each of those cross frames serve as a bracing element for the beam, okay? So here's the beam. So the beam is this long, so this is the length of the beam, but these segments, these are the unbraced length. This would be LB for that column. So in bridges, the most common example of discretely braced elements are girders with their associated cross frames. The cross frames serve as the braces. That's what you find in bridges. In buildings, what you find is the other beams, okay? So for example, if you look at a floor system in a commercial structure, you find that, okay, so we have here a girder, and this iron worker is sitting on the girder, and we have these beams framing into that girder. Those beams are acting as braces for this girder, okay? That's what's going on, okay? And to be clear, what we are interested in what we're interested in from a bracing perspective is, do those braces prevent the compression flange from moving laterally? So for example, if I'm looking at this element here, or this system here on the left, so here's a support, and then we got a support all the way down here. So the bridge is bending downwards, smiley face bending, the top is in compression, the bottom is in tension. So when we're designing that brace, we want to ensure that the top of the beam is prevented from moving left or right. Okay? That's what we're interested in from a bracing perspective. Okay? The reason why is because of lateral torsional buckling, which we're going to talk about here in a bit. Now, what you're going to start to see somewhat soon are some schematics that kind of look like this. So, for example, let's take a look over here on the right. So this is a simply supported beam with a uniformly distributed load. I've got to believe that that is you are all comfortable with because of what we did last semester in structural analysis. But you're starting to see something that's a little different. You start to see these little X's that I've drawn here. Okay? So imagine, for example, that this beam is 30 foot long. And every 10 feet, I have a brace framing into that beam. Okay? So to be clear, for this beam, the beam would be 30 foot long. The unbraced length would be 10 foot long. And to keep it really simple, the 30 foot length is what I'm interested in from a structural analysis perspective. The 30 foot is what I'm going to use to compute support reactions, draw shear diagrams, draw moment diagrams, etc. But it is the 10 feet that I am going to use in the formulas that I explain later to compute capacity. Okay, does that make sense? So that's a really clear differentiator between what you're going to use the 30 foot for versus what you're going to use the 10 foot for. Okay, now the braces serve. What do they do? What are they actually doing? Well, I say that they serve to quote unquote strengthen the beam. In other words, that as the distance between those braces increase, in other words, as those braces get further and further apart, the beam gets weaker. Or on the flip side, if I start including more and more braces, the capacity goes up. Okay, so does that make sense? Like, and that has a direct analogy to what we were talking about with columns. Like, as the distance between braces for columns increases, the capacity went down because it's more susceptible to buckling. Same thing here. Okay, but the big thing I want you to keep in mind is that no matter what, the capacity cannot be larger than MP. MP is always the maximum. Okay, now, what are we initially going to be talking about in this class? Our initial class of beams, what we're going to consider are continuously braced beams. So these are beams that we assume have bracing everywhere, like an infinite number of braces all along the span. And some of you probably think, oh, come on. When do you ever have an infinite number of braces across the span? A good example is this, okay? So this is an example of a steel beam and a concrete composite deck poured on it. Every beam in this building is like that. So we have a steel beam, we have some shear studs. Typically in building design, we lay the stay-in-place metal formwork and we shoot the studs directly through the formwork into the flange. And when I say shoot, what I mean is weld. I'm saying that we have a stud welder, we take the stud, we load it into the stud gun, we load it, and it shoots the weld right through the pan, right into the top flange. Okay, we have a series of those studs along the top flange, and then what do? We get out our concrete truck and we place the concrete, and the concrete cures, and that concrete cures and it locks with those shear studs. Okay, how many of you have ever been on a DOH construction site and seen the concrete deck placed and seen these shear studs I'm talking about? I'm just curious. Okay, so probably if you were on a DOH bridge site, probably the first thing you were thinking is, there are a boatload more studs than that on the beam, am I right? In bridges, we use a lot more studs than we use in buildings because bridges are subjected to fatigue. They have loads on and off, etc. So you need more studs in bridge design than you do in building design, where we're not worried about cyclic loading to that scale, if that makes any sense. Okay, so this is a real-world example of a beam that is continuously braced, that it can't move left or right at all because it's literally locked in with the concrete deck, and the concrete deck is preventing that lateral translation. So this is a continuously braced beam. So what is the flexural capacity of a continuously braced beam? It's MP. It's the maximum flexural capacity. Okay? Now, let's break this down a little bit. Okay? Now, if we're analyzing a steel beam, we have ultimately 3 limit states that we need to withstand. We need to check. We need to ensure that it has adequate moment capacity. We need to ensure that it has adequate shear capacity. And we need to ensure that it doesn't deflect too much. Okay? So there's a lot here on this slide, but so I'll take my time with it. Okay? Now, a couple of notes here. There are some more limit states that you might have to consider if you're looking at some more advanced types of designs, things like floor vibrations or ponding or fatigue or stuff like that. But for the vast majority of structural steel beam designs for standard applications, these are really the 3 limit states that you need to be considering. Okay? Now, these conditions are what we're going to have to ensure regardless of if it's continuously braced or discretely braced. We have to ensure adequate moment capacity, adequate shear capacity, and that it meets deflection requirements. Now, a couple of notes to clarify this. The first thing I want to talk about is the shear capacity. I am not going to discuss how to compute shear capacity until near the very end of the semester. And what we're going to do is we're just going to use a design aid that I'm going to show you here in a little bit to look up shear capacity. But there's another reason why we're not going to talk about it right now, and the reason is it doesn't matter. Okay? What you're going to see when we start doing problems with steel beam design is that we're going to start looking at the shear, and we're going to find that the beams have, I don't know, 20 kips in shear, but they can withstand 190 kips in shear. Like, the numbers are just going to be way different, such that shear is just not a problem. It just doesn't really matter. How many of you have had reinforced concrete? So you know that shear design in reinforced concrete is a thing. There's stirrup design. You have to space the stirrups out. It is a whole thing in reinforced concrete design. In here, shear design doesn't really matter all that much. Now, I want to qualify that statement by saying that in buildings, shear doesn't matter. In bridges, it is a way different story, particularly if you're talking about plate girders, because you're actually selecting the size of the flange, the thickness of the web, etc. So you have to really go through the details there. But for building design, for shear, ends up not really being a really big deal. The other thing I will say is that deflection limits are much more straightforward than they are in reinforced concrete. So if you've had reinforced concrete, you know that there is a difference between immediate deflections and long-term deflections, because as the load sits on the beam for a certain number of time, you start to experience creep and other effects that change the deflections over time. We don't need to worry about that in steel, because steel's material properties are largely pretty consistent as a function of time. So that part's easier too, okay? So I'm just saying that you're going to see some nasty, I guess this is my roundabout way of saying, you're going to see some complicated equations, but it's easier than concrete, I think. So, sorry. Okay, let us turn to table 3.2. This is a very important reference. It is a very important reference, so much so that this is another one of those references that's in the NCES FE reference manual. When you use when you take the FE, they include this table in the manual because you can't design steel beams without it. Okay. There are a number of terms in this table. By the time we are done with this semester, you will understand what all of them are. Like, right now, you don't know what LP and LR are, or the beam factor term, the BF term. You don't need to worry about that right now. Don't worry about it, okay? What you need to worry about understanding is the ZX terms, the VMP terms, the moment of inertia, and the shear capacity. Now, you will probably never hear me call this table 3.2. You will probably hear me call this the ZX tables. Why? Because it's the title of the table, selection by ZX. But more specifically, just start thumbing through the table, and what do you see? You see that the sections are organized by their ZX term. So here's essentially what happened. Remember how there's an Excel spreadsheet that you can download that contains all the W sections, right? You know how in Excel you can sort by a given column? So take that column, sort by ZX, that's what order these are in. It's that simple. What's that? Oh, yes, you should definitely tab this table. Absolutely. Now, so in this table, you can just look up the shear capacity. And so in this table, we're going to use that to look up the shear capacity for the majority of the semester. But again, as you're going to see, shear doesn't really matter all that much. Now, here's something I want to make sure y'all are paying attention to. Notice how, if you start thumbing through that table, you notice how they're in groups. You know how the W sections are in groups? Like there'll be a group of like 10 of them, and then a group of 5 of them, and then a group of 12 of them, then a group of 13 of them. Y'all see that? What can you tell me about the top row in all those groups? It's bolded, right?
Yeah.
Every time. Now, I want you to take any one group, find a group in that table that has a few sections in it, like not one that's just one by itself, but one that has like 6 or 7 sections in it. And I want you to look at that group. And I want you to tell me, is there something about that bold row that's worth bolding? Why is that top row bolded if you look at that group? It's the lightest. Do y'all see that? If you look at a given group, look at the pounds per foot, and you will find that within that group, that is the lightest section, okay? Those are the most optimal sections as a function of ZX. So like in design mode, what we will do is compute the required moment capacity But instead of just picking any section, we will pick one of the bold sections, because the bold sections are the lightest within that group. Does that make sense? So that's just something to think about for later. Okay. Now, a couple things about this. So we have the ZX. So this term right here, phi MB, or phi B MPX, that is just the plastic moment capacity. So all you're doing is taking this times Fy and dividing by 12 to get it into foot kips, and then your phi value is 0.9. Phi is going to be 0.9 for bending. Okay. Now, before we get into some later stuff, let me take a step back. Let me stop for a second. I don't want to get too far ahead of myself. Does anybody have any questions about what we're talking about so far? It's all straightforward? Okay. Now, I want to go back to something that we talked about really early on in the semester and sort of, jog the memory, as it were. So, if you remember, early on in the semester, I discussed that we had strength limit states and we had service limit states. And if you remember, strength limit states are all about safety. Like, if we violate a strength limit state, we're talking about the structure failing, falling down and killing people. Okay? And so, in order to ensure the safety of the structure, we use load factors, we use phi values, etc. Right? That is what those load and resistance factors are. Okay? That's not what a service limit state is. A service limit state it deals with day-to-day performance, just making sure the structure is performing its intended function. So things like slenderness, like L over R being less than or equal to 300. Things like bolt spacing and weld limits. Things like deflections in beams are service limit states. The crystal clear point that I want to be clear about is that when you are assessing service limit states, you do not factor the loads. You do not factor the loads when you're dealing with service limit states. So when we look at deflection limits, we do not use load factors, okay? So if you start doing 1.6 times the live when you're looking at live load deflection limits, don't do that, okay? That's not good, okay? So in order to analyze beams, y'all are going to have to draw some shear diagrams and some moment diagrams. It's like, oh man, remember all that stuff you did last semester? And you're like, come on, Dr. Mike. That was so 2022. Like, do we really have to do that again? Kinda. Y'all remember the very last thing that we did in structural analysis when we were looking at analysis aids? When I would say, derive these formulas that you could use to analyze the beam for you. Y'all remember that? Maybe what you ought to do is you ought to turn to table 3-23. There's another tabbable page for you. Starts on page 3-208. This is a really, really useful guide. What this does is this delineates analysis, say, for shears, moments, and deflections for standard load cases. So if you don't want to draw a shear diagram or draw a moment diagram, no worries. All you have to do, break out table 3-23 and use the appropriate case. So for example, if I have a simply supported beam and a uniformly distributed load, I know the shear goes like that. I know the moment goes like that. I know the maximum moment is WL squared over 8. I know the maximum shear is that the reaction, WL over 2, etc. Okay? So it will make the structural analysis a whole lot easier. Now, I'm sure some of you are saying, wait, Dr. Mike, if we had all these formulas, why didn't we learn all that structural analysis stuff last semester? Well, this is only for very straightforward load cases. In the real world, you might get something a little bit different. You need to be able to analyze the structure. So, then again, we structural engineers try and do what we can to keep things simple. Any questions? Let's do a problem together. Okay? So I want to analyze this beam shown in order to assess its performance. Okay, so I have a W21 by 62. It is made of A992 steel, and I want to Here, I'll pull this up here. I want to assess whether or not the beam has adequate moment capacity, adequate shear capacity, and I want to assess whether or not the beam meets an L over 400 live load deflection limit. There's a lot to chew on that. We'll take that one later. Okay. Now, it's a simply supported beam with a uniformly distributed load, and one of the things I said here in this box, which is really important, is that the dead load shown does not include the self-weight of the beam. So what we would say is that this dead load is superimposed, okay? So a superimposed dead load is on top of the beam's self-weight, okay? And so I use that term because I throw that term out on the homework assignment. So for what's superimposed, that's what's superimposed. So we're going to determine that the beam has adequate moment capacity, adequate shear capacity, and an L over 400 live load deflection limit. Okay. Now a couple things about the W21 by 62. Let's put that over here. Ooh, I don't think this likes the right side of my screen, this pen. What is ZX for the W21 by 62?
144.
144. Okay, hold on. That's going to bug me. Hold on. I'm not going to like that. While we're at it, what is the moment of inertia? Is this one of the bolded rows?
Yeah.
Okay. Now notice these properties you could get in table 1-1 in the very beginning of the manual. But
1330.
1330 units.
Inches to the fourth.
Okay. Now, what is the self-weight? And I'm going to use W sub naught.
0.062.
0.062 what?
Kips per foot.
Kips per foot. Okay. So to clarify, the self-weight of the beam is 62 pounds per foot, or 0.062 kips per foot. Okay? Okay. Now, the first thing I want to do is I want to do the structural analysis. Okay? And I'm just going to level with you. I am going to do this inefficiently. Okay? And the reason I'm doing it inefficiently is because you're going to need to do it this way on your homework assignment. And you'll see what I mean when we get to that. Okay. So, for the dead load, this is what I have for the dead load. I have a beam. I have this. I have a load like that. Okay? And the dead load plus the self weight is a total of what? 1.062 kip per foot. And it is over a distance of, how long is this beam? So help me out. How do I compute the dead load moment? How do I do that? Well, I could compute the reactions, draw the shear diagram, draw the moment diagram, get the maximum moment on the moment diagram, and use that moment. Or I could just look up the formula. What is the formula for a simply supported beam subjected to a uniformly distributed load? There you go. And that, if you remember correctly, or if you remember last semester, that's the one I had you all derive on your own. It's almost like I knew we were going to use this one day. And so what do we get for that? Say it again.
135.9.
Do I have a second?
Yeah.
Okay. All right. What about the shear? How do I compute the dead load shear? What's our expression for shear? Do I need to turn the lights on? That help.
W/2.
WL2. I know the writing in that table is a little small. Where are we getting to that?
16.99.
Say it again, 16.99?
Yeah.
Do I have a second?
Yes.
Okay. Now that's the dead load. What about the live load? Now, the live load is also a simply supported beam with a distributed load. .5 kips per foot. .32 feet. So it's the same case. So what do? I compute the live load, compute the WL squared over 8. And I can walk you all through this one because at that point it's the same calculation. So this one ends up being 192. And this one is 24. Okay. And then with these, what I'm going to do is I'm going to say, okay, now give me the factored load. So MU is 1.2 M dead plus 1.6 M live. So that is, I think that's 470.3.
Yeah.
So here's what I'll do. I'll write it over here. I'll say and then VU okay, and so what is VU?
58.98.
Yeah, that's close enough. All right. Okay. Now, I'm sure that there's some of you in here that are thinking, Dr. Mike, you did that way too complicated, because couldn't you have just factored the loads and then did WL squared over 8 and WL over 2? Because that would have been a lot less button crunching. You are 100% right, okay? The only reason I didn't do that is because the only way that works is if they are both simply supported beams and both uniformly distributed loads. What if I have this? What if I have a simply supported beam and I have a dead load like this, but then I have a live load like that, okay? Then I can't just factor the loads. I have to treat them separately. And if some of you are thinking, well, why don't I just take the load and divide it by the length and turn it into a distributed load? If you're thinking that, I want you to take your hand and do that. The answer is no, okay? Because what you're doing is changing how the moments are distributed on the beam. This is a structural analysis boo-boo. And we talked about this last semester. If I have a beam, what is the worst scenario? Lumping all the load in the middle or spreading it out? It's lumping all the load in the middle, okay? This says the live load is lumped in the middle. If you take that load and spread it out, you're being unconservative and potentially producing an unsafe design. Does that make sense? So don't do that, okay? So what you would have to do here is you'd have to say, okay, the dead load is WL squared or WDL squared over 8, and then the live load is PL over 4, because that's the expression for maximum moment under a point load at midspan, okay? So that's why I'm saying I want you to get the habit of handling them separately, because if they are different load cases, then they are going to be separate expressions, okay? Does that make sense? So, okay. Okay. All right. So, but going back to this problem, let's just be clear, okay? So, MU, so let's do this. So we'll do, just to sort of track what we've got going on. So moment, shear, deflection. Okay, so moment, we know that MU is, what is that, 470.3. We know that VU is 58.8. Okay, so let's just use that as our sort of tally, as it were. Okay, now for moment and shear, what we're now going to do is we're going to look at capacity. Okay, now if we have a continuously braced beam, the way that we compute Mn, or phi Mn I should say, is phi Mp, which is Fy Zx. We just did that last time, okay? So, how do we do that? Phi is 0.9. Fy is 50 ksi. This is 144 inches to the third. And then what I'm going to do is convert by dividing by 12. Okay? So check this out. Tell me what you get. $540. Do I have a second on that? Yeah. Okay. So is the beam safe under bending? Yeah, it is. Do y'all remember how to compute an efficiency? An efficiency, load over resistance, right? What is load over resistance over here? What is that?
Just so we're clear, we're doing MU top number.
Yeah, yeah, the load over the resistance, right? Like the Price is Right.
0.87.
0.87. Get 3 decimal places. Give me 3 just for a second.
0.871.
0.871. Okay, so 0.871 is its efficiency. So I'm going to introduce you to some terminology. In the land of bridge engineering, we would call that a performance ratio. So the performance ratio under bending is 0.871. It's the same thing. So I'm just introducing you to some terminology. So is this beam an efficient beam? It's not bad, you know. Remember, we're going to go to a group and select the lightest beam anyway, so there's going to be some conservatism in that, okay? Now, so what I'll say is phi-mn is 540, mu is 470, bless you, 0.3, so therefore, that's okay. Okay. Now, what about shear? What is the shear capacity of the beam? Well, how do we compute that? We're not going to compute that. We're going to look it up right now. What is the shear capacity of the beam? And we're going to look that up in table 3.2. For a 21 by 62, what is it? $252 kips. Everybody else find that for the 21 by 62? So phi-vn is 252 kips and Vu is 58.8 kips. Is that being good? Is that good? Yeah, it's good. What's the performance ratio for that? .233. So we call that a performance ratio for shear. And again, they end up, like the performance ratios for shear, they're just really low. Like the steel beams in buildings, they just have a lot of shear capacity. Except for, I mean, there are some instances like with transfer girders and whatnot, but most standard everyday beam design, shear ends up not being a problem. Now, for deflection, okay, so let's talk about deflection. Okay? Now, specifically in the problem, what the problem said is that we are doing a live load deflection check, okay? So, So remind me, we had a live load of 1.5 kips per foot. We have a length of 32 feet. We have an E value of 29,000 KSI. And we have a moment of inertia of 1330 inches to the fourth. How do we compute the live load deflection according to table 323? I believe it is 5WL to the fourth over what? 384 EI?
Yes.
Yeah, that was, yes.
I don't even know what beam is.
What's that?
I haven't even found the beam.
We were just looking at it.
No, I wasn't.
Maybe next time.
Maybe next time. All right. Now, so in order to compute that, we have 1.5 kips per foot. The length is 32 feet to the fourth over 384, 29,000 KSI, and then 1330 inches to the fourth. Anybody see a problem? Units. Y'all remember when we computed deflections in structural analysis, we had a magic number that we used? 1728. That it's a magic number that converts cubic inches, cubic foot. It's like that stuff that we did last semester has value. It's crazy. So what are we getting here?
0.918.
0.918
Yeah.
inches. Do I have a second on that? Do I have a second? Did you not bring your Casio FX 115 ES Plus or similar scientific calculator?
I got it. It's just
He
back
can't be bring it out and be engaged and with us in this wonderful world of CE 414 structural steel design here at Marshall University. I'm heartbroken. Do I have a second?
Yep.
Okay, thank you.
Yep.
They seconded me on that one.
Yep, so did I.
Oh, you did. Well, then you can help me on the next one. All right.
Ooh, get it out.
So the maximum deflection is specified as L over 400. And this is a common way to specify deflection limits, as L over some number. Okay? So what we're going to do is we're going to say 32 feet over 400, but we are also going to convert that so that we have a usable quantity at the end of the day. Okay? And what is that?
0.96.
0.96 inches. Okay? So our maximum deflection is 0.96. Is this beam sufficient? What is the performance ratio under deflection?
0.956.
So what's interesting is out of moment shear and deflection, what is actually the most important limit for this beam? What's actually governing the design?
Deflection.
The deflection. So this beam has oodles and oodles of capacity, and we actually had to make it bigger just to make sure it doesn't deflect too much. It's very interesting how service limit states might end up actually governing your design. Okay, I know we're running short on time. I do want to pull up the next homework assignment to make a point. So here is the next homework assignment. I've given you a cantilevered beam with a distributed load and a point load at the end. Okay? So the 2 points I want to be clear about is how we computed the moments of dead load and live load and the shears of dead load and live load separately, you definitely need to do that with this problem. You can also refer to table 323, but I want to be absolutely crystal clear. WL squared over 8 and 5WL to the 4th over 384 EI, they are not going to work on this problem because this is not a simply supported beam subjected to a uniformly distributed load. We have a cantilever beam. We have a cantilever beam with point loads and distributed loads. You've got to go through the process and categorize those correctly. But we have a live load deflection limit of L over 180, and we have a W24 by 76. What's that?
So where the deflection is like, or
Hold on.
so the moment shear and deflection is basically saying like the beam can move everything, but it's not going to fail. But then the deflection is saying it can move with just almost an inch, but you don't want it to move more than that.
Yes.
So like it's saying it won't. Everything else will hold it up, but it might bend. So you don't want it to bend that much.
Yes. There is a difference between whether or not the beam is going to actually, fail and collapse and kill people versus if it's literally deflecting too much. So like as an example, L over 360 deflection limits came from plastered roofs, because if you start failing L over 360, you start cracking the plaster. Cracking the plaster does not mean the beam is going to fall down and kill people, but you don't want to crack the plaster. So I'm saying, quote unquote, we needed to upsize this beam to make sure we didn't crack the plaster. That's what I'm saying. Sound good? All right. You're going to be my calculator guy next time. That's all I got. I'll see you all on Monday.
Yeah.